Welcome to this comprehensive guide on understanding game architecture, a crucial foundation for building efficient, scalable, and maintainable games. Game architecture serves as the blueprint for how a game's code and systems are structured, directly influencing its performance and long term viability. For beginners, grasping these fundamental components and design patterns is essential for effective game development within powerful environments like Visual Studio and Unity 3D. This video will provide a step-by-step, beginner-friendly guide demonstrating key concepts and workflows to help you build better games. Let's begin by exploring the core components that form the backbone of every interactive game experience, from rendering to input processing. Every game comprises essential components such as a graphics engine, responsible for rendering all visual elements, and an audio engine, managing all in-game sounds and music. The graphics engine handles everything from textures and models to lighting and post-processing effects, bringing the game world to life. The audio engine manages sound effects, background music, and voiceovers, ensuring an immersive auditory experience that complements the visuals. It also includes a rendering and vision input engine, handling how the game is displayed and how player input is processed from various devices. Input, output, or I/O devices like keyboards, mice, and gamepads are crucial for player interaction, translating physical actions into in-game commands. Dynamic Link Library, or DLL files, with their associated drivers and device APIs, are crucial for enabling hardware interaction and extending game functionality. These DLLs provide access to system-level functions and external libraries, allowing games to leverage specialized hardware and software features. All these diverse components work in concert, communicating seamlessly to create the rich, interactive experiences we expect from modern video games. Next, we delve into the architectural layers that organize a game's codebase, promoting clarity, modularity, and ease of development. Game architecture shares similarities with general software architecture, but incorporates game-specific elements like levels, action sequences, and engaging visuals. Unlike typical applications, games often have unique requirements for real-time processing, complex state management, and dynamic content loading. Abstraction layers are vital for organizing the codebase, making it more manageable and easier to understand for developers working on complex projects. These layers hide implementation details, allowing developers to focus on specific functionalities without being overwhelmed by the entire system. A typical game architecture often includes three primary layers: a visual layer, a game logic layer, and a data layer, each with distinct responsibilities. The visual layer consists of scripted game engine components, such as Unity's MonoBehavior, which directly drive what the player sees on screen. This layer handles rendering, animations, user interface elements, and all other graphical representations that form the player's view of the game world. The game logic layer, further divided into visual game logic and pure game logic, handles state management and the core rules of the game. Visual game logic dictates how game objects behave and interact within the visual space, while pure game logic manages the underlying game state and rules. Finally, the data layer is responsible for managing all game data, from player progress and save states to item inventories and configuration settings. This layer ensures data persistence and integrity, allowing players to save their progress and game settings to be loaded consistently. These distinct layers promote modularity, making the code significantly easier to manage, update, and debug over time, especially in large teams. Design patterns offer proven solutions to common architectural challenges, providing a structured approach to game development that enhances flexibility and reusability. The Model View Controller, or MVC, pattern separates game logic into three interconnected parts, enhancing separation of concerns and improving code organization. The model handles data and business logic. The view manages the visual representation and user interface, and the controller acts as an intermediary between them. This separation allows for independent development and modification of each part, reducing the impact of changes on other components. The Entity Component System, or ECS, pattern is another popular choice, especially prevalent in high-performance engines like Unity and Unreal Engine. ECS consists of entities, which are game objects, components, representing attributes and behaviors, and systems, which manage and update these components efficiently. This pattern promotes data-oriented design, leading to better performance and more flexible game object definitions. The observer pattern allows components to react to game state changes without tight coupling, significantly enhancing flexibility and reducing dependencies. For example, a UI element can observe a player's health changes without needing direct references to the player's health script. Implementing these patterns leads to more organized, maintainable, and scalable game projects, making them easier to extend and adapt in the future. Adhering to best practices is crucial for developing high-quality, robust game architectures that stand the test of time and complexity. Begin by creating a detailed game design document, or GDD, outlining the game's vision, core mechanics, story, and target audience. The GDD serves as a living document, guiding the entire development process and ensuring everyone is aligned with the game's direction. Complement this with a technical design document, or TDD, which details the technical implementation, architecture, and specific technologies to be used. The TDD translates the game design into actionable technical tasks, providing a roadmap for engineers. Solid principles, single responsibility, open/closed, Liskov substitution, interface segregation, and dependency inversion promote reusable, maintainable, and less buggy code. Applying solid principles helps create flexible and robust software designs that are easier to modify and extend without introducing new errors. Modular architecture, where systems are independent and communicate through well-defined interfaces, is also paramount for large-scale projects. This approach allows different teams to work on separate modules concurrently, speeding up development and reducing integration conflicts. Avoiding code duplication by abstracting common logic into reusable functions or classes significantly reduces bugs and simplifies updates across the codebase. Reusable code components lead to a cleaner codebase, fewer errors, and faster development cycles for future features. Version control systems like Git are indispensable for team collaboration, tracking changes, and providing a safety net for disaster recovery. Git allows multiple developers to work on the same project simultaneously, merging their changes efficiently and resolving conflicts. Automating build and testing processes through CI/CD pipelines ensures consistent quality, faster iteration cycles, and early detection of issues. Continuous integration and delivery streamline the release process, allowing for frequent updates and rapid deployment of new features. Profiling the game's performance on target hardware is critical for identifying bottlenecks and ensuring a smooth and enjoyable player experience. Optimizing performance involves analyzing frame rates, memory usage, and CPU load to ensure the game runs efficiently on various devices. Unity 3D offers specific tools and practices that greatly enhance game architecture, leveraging its powerful engine capabilities for efficient development. Developers should leverage scriptable objects to create modular game architectures, avoiding tight coupling and the dreaded spaghetti code. Scriptable objects act as data containers that can be shared across multiple game objects and scenes, promoting reusability and reducing redundancy. They build a robust foundation to connect multiple game systems efficiently, acting as event broadcasters and configuration holders. Best practices also involve separating persistent domain components into standalone, testable scenes, improving organization and testability. This allows for easier testing of individual systems and ensures that core game logic persists across level changes. Ensure each monobehavior component handles a single, distinct feature to maintain clarity, reusability, and ease of maintenance. Avoid creating God objects that try to do too much. Instead, break down complex behaviors into smaller, manageable components. Prefer composing game objects from multiple components rather than integrating all logic into one monolithic script, following the composition over inheritance principle. This approach makes game objects more flexible and easier to modify, as you can swap or add components without altering existing code. Effective coding practices include using structs instead of classes where possible to minimize garbage collection costs and improve performance. Structs are value types and are allocated on the stack, reducing pressure on the garbage collector compared to heap-allocated classes. Employing object pooling, especially for frequently instantiated game objects like projectiles or enemies, significantly improves performance by reducing allocation overhead. Object pooling reuses existing objects, avoiding the performance hit of creating and destroying them repeatedly during gameplay. Seamless integration between Visual Studio and Unity is key to a productive development environment, enhancing the coding and debugging experience. The Visual Studio tools for Unity, or VSDU, provides powerful features like IntelliSense, advanced debugging, and efficient code navigation. IntelliSense offers smart code completion, helping developers write code faster and with fewer syntax errors, improving overall coding efficiency. These tools enhance productivity by allowing developers to write code quickly and with greater precision, minimizing errors and speeding up development. Visual Studio offers a premium debugging experience, enabling developers to set breakpoints and evaluate variables directly within their game code during runtime. This powerful debugging capability allows for precise identification and resolution of issues, significantly reducing development time. Unity's engine integrates seamlessly, allowing for the creation of diverse 2D and 3D games and interactive content across multiple platforms with ease. Overall, understanding game architecture involves grasping core components, utilizing design patterns, following best practices, and leveraging tools like Visual Studio and Unity effectively. This comprehensive approach equips beginners with the essential knowledge to build scalable, maintainable, and high performing games that deliver exceptional player experiences.